Hi all, today's topic is equilibrium criteria. Before moving to the topic, I would like to give you the introduction about the power system stability. What do you mean by the stability? Stability is the power in the power system is defined as the ability of the power system to return to the stable operation when it is subjected to a disturbance. There are three types of stability studies: steady state, dynamic, and transient. Steady state stability is the stability of the system when subjected to gradual or relatively slow changing load. Dynamic stability is the denotes as the artificial stability given to a system by the action of automatic control devices, whereas transient stability is subjected to major disturbances such as transmission system faults, sudden load changes, loss of generating units, or line switching. Now, we'll move to the topic equilibrium criteria. Transient stability analysis of the simple system can be performed by using a simple criterion called equilibrium criteria. There are two situations for the change in torque angle with respect to time during the transient state of a power system. Situation 1 is that the torque angle may increase to a maximum value and then decrease to a stable value. It refers to stable system. Situation 2 is that the torque angle may keep on increasing indefinitely. It refers to unstable system. So, the system is stable. To be the system is stable, the positive accelerating area is equal to the negative decelerating area for a finite change in torque angle. This stability criteria is called equilibrium criteria. Now we'll move to the applications of equilibrium, in which there are 4 applications are mentioned in your syllabus. Here I am going to explain the only one application in this video. That is first application, transient stability analysis for a sudden change in the mechanical input. For this, we are considering a single generator feeding energy to infinite bus. Generator, as you all know, it converts mechanical energy to electrical energy, and infinite bus is having constant voltage and frequency. So from this single line diagram, you can find out what is the electrical power transmitted by the generator. It is E double dash V by X sine delta. When delta is equal to 90 degree, we will get the maximum power, which is referred as P max. P max, where P max is E dash multiplied by V upon X. Let the figure gives you the power angle curve of the generator. Let the generator be operating in steady state with the torque angle delta naught. So this is the torque angle delta naught at which the generator is operating at steady state, that is at the point A. At point A, steady state condition, mechanical input will be equal to electrical output. Therefore, PM naught equal to PE naught, which is equal to P max sine delta naught, where P max is the steady state maximum power it can transmit. That is, this is the maximum power here. The peak value of this power angle curve is a P max. P max sine delta naught equal to PE naught, which is equal to PM naught. Now, as per the applications, we are going for a sudden change in the mechanical input. So, by some adjustment in the prime mover, we can increase the mechanical input from PM naught to PM1. Since the mechanical power is more than the electrical power, mechanical power is PM1 and electrical power is PE naught. As PM1 is greater than PE naught, the generator will have an accelerating power which is given as PM1 minus PE naught. Due to this accelerating power, the rotor speed increases and also rotor angle increases. So rotor angle increases from delta naught to delta 1. This increases the electrical power generation. So corresponding delta 1, you can see the point B. That is, electrical power output in the power angle curve is shifted from point A to point B. So at point B, electrical power output is PE1. But at point B, because of the inertia of the rotor, it will make the rotor to oscillate with respect to point B. That is, the torque angle will continue to increase from delta 1 to delta 2, and the electrical delta 1 to delta 2, it will increase, and the corresponding electrical power output will be PE2. You can see here, this is the electrical power output PE2. Now, with respect to the mechanical input power, electrical power is more. That is, PE2 is greater than PM1. This causes the generator for a negative accelerating power, that is called decelerating power. Thus, the rotor speed decreases. So, from point B to C, even though the torque angle is increasing, the rotor speed will decreases. So, you can see that the rotor oscillates between the point A and point C before settling to point B. This point C is decided by the damping of the system. Depends on the damping of the system, point C to which point it has to be oscillated, that it will be divided, depends on the damping of the system. At point C, the speed of the rotor will be equal to the synchronous speed. So till that point, it will be oscillating from point B to point C. So the steady state will be happening soon, for the stable system will be settled at point B after oscillating from through the point A to C. So from this power angle curve, we can see that the system is stable only if the area A1 is equal to area A2. What is area A1? Area A1 is the acceleration area, since input power PM1 is greater than the output power PE0, whereas A2 is the deceleration area, since electrical output power is greater than the mechanical input power. Electrical power is PE2 greater than PM1. Therefore, the rotor decelerates. So, to satisfy the equilibrium criteria, A1 should be equal to A2. So, by applying the limits of the torque angle, it is given that A1 is equal to the integral delta naught to delta 1, PM1 minus PE d delta. This is the accelerating area, whereas A2 is integral delta 1 to delta 2, PE minus PM1 d delta. This is the decelerating area. So, to satisfy the equilibrium criterion, A1 should be equal to A2. This slide gives you that there is an upper limit for increase in mechanical input power. In the last slide, we have analyzed what will be the transient stability analysis for a sudden increase in mechanical input power. So, here there is a maximum limit for the increase in mechanical input power. So what should be that maximum limit for the mechanical power input? The limiting condition is that the mechanical power is increased to a point where area A1 equals the area above PM1 max. So initially, at a steady state torque angle at operating A, PM0 is the mechanical input power, which is equal to PE0, and by the adjustment of the prime mover, we are increasing the mechanical input power to a value. So what should be the limit of that input mechanical power? That is, it is given as PM1 max. So this is the limit of the mechanical power. How the limit is identified is that this area should be equal to A2. A2 is the area above PM1 max. So this area A1 should be equal to A2. Under this so the corresponding delta will be delta 1 max, and upper limit of the delta will be delta 2 max, and delta 2 max is given that it should be pi minus delta 1 max. This is the condition to be followed, so that we can say that A1 equal to A2. In case any further increase in PM1 max, if we are increasing from this point till further to the positive side, if you are increasing, you can see that the area A2 will be lesser than area A1, which cause the system to remain in unstable state. Therefore, the limit, the maximum limit to increase the mechanical input is PM1 max minus PM0. This will be the maximum limit. It can, the prime mover or the system can increase the mechanical input power for the system to be stable. This PM1 max, this is called the transient stability limit of the system, whereas this PM, that is the maximum power it can, a PM is here you can see the PM, that the maximum power it can be transmitted. This is the triple SL, that is called steady state stability limit. So from this power angle curve, it is very clear that steady state stability limit PM is always greater than transient stability limit PM1 max. Hope you understood this section.